I will now discuss a problem, since so far every problem was given a name. So let me give this a name. Mass on a moving wedge. So this is the wedge, which has a mass m. This angle is theta, and here is the other mass m. The whole thing rests on a horizontal surface, and there is the gravity down. And we shall study this system. This system is different from the systems studied so far, because the system has two accelerations. One is the acceleration of the wedge, the other one is the acceleration of the mass. In the problems before this one, we had seen systems, one mass or two masses, but they had the same acceleration. Okay? So for example, consider an Atwood machine, M1, M2. For example, if this goes down with acceleration a, this goes up with an acceleration a. So essentially they have the same acceleration. But here things are different. And this is a problem where I will increase the sophistication of it as we go along. So as a warm-up, let's make a warm-up. Athletes and basketball players, before the game starts, make a warm-up. So it's a warm-up like this. Let's study the case, for example. Instead of a wedge, we have a fixed inclined plane. And to begin with, we keep things life simple. There is no friction. So how does this thing move? The condition for motion is that it is allowed to go only along this line. So we isolate the body and study the forces on it. Here's the mass m. There is the gravitational force down, mg. And there is the reaction of the plane on the mass. And since there is no friction and it's only perpendicular, r. And this angle is theta. So it is pulled down along this axis by the force mg sine theta, minus, there is no force that's opposing, so it is equal to ma prime, or ma, m's cancel, so a is g sine theta. You can find the reaction force simply r equals mg cosine theta. So that's one warm-up. Another simple problem we can ask is this. Suppose I have a mass m, wedge, and this one, angle theta. I am applying a force F0. What should F0 be so that m and m move together without any relative motion? Namely, they move together. So it is as if the situation is like this. So this is a mass m plus m. F, clearly, F equals plus ma. F is, what is F? So that, well, we can't solve from here because we don't know F0 and we don't know, therefore, this A. Therefore, we need to go isolate this body. And now, this body, like here, has no relative motion. Therefore, it's accelerating to the right with the acceleration a. So if you put the forces again, mg down, this is the r. So the component of this force along the horizontal gives it the acceleration. R sine theta is equal to ma. And the vertical component will balance it along the vertical direction. So r cosine theta is equal to mg. Now we can solve two equations, two unknowns, a and r. Just divide, r's cancel, therefore m's cancel. Therefore, a is equal to g tangent theta. A is known. Therefore, we can find f0 is equal to m plus m g tangent theta. Okay. So these are the warm-up exercises. Now we come to the general problem that we have two masses. Okay, I am erasing this. All right. Now we study this problem. There is no friction here, no friction here. And what is the general motion? Now, let us isolate the bodies and look at the forces. The kinematical constraint on this body is that it is moving to the right or to the left. So I'm not interested in the vertical motion of m, but so this is r. This is the reaction force of m on m. And since g is down, I don't care. Here is m. So this is theta, this is theta. Hence, r sine theta is equal to m times a. Okay? I am taking a like this. So obviously, mass m will move to the left. Now, how to study the tricky point is how to study the motion of mass m. The problem is with the kinematical constraint. M is constrained to move down the plane along this line. But this thing is moving to the left. Therefore, if you look from outside, it is not going down the inclined plane with angle theta. So instead, if you put your observer that observes this phenomena, let us put the observer, here's it, let us put the observer here, okay? Now the observer is on the wedge, but the wedge is accelerating, okay? So why do we use this system? Why do we put our observer into the accelerating system? This is to simplify the kinematical constraint. In the accelerating system, life is simple. This is simply going down the inclined plane, inclined with an angle theta. But there is a price. The price to pay is that you have to add, in addition to the real applied forces, a fictitious force. Sometimes you call it ghost force. So let's draw the force diagram. Isolate the mass m. Here's mass m. Okay. Okay, here's the gravity down, mg. Here's the reaction force r. And since it is going to the left, since the wedge or our observer is going to the left, it will see a force acting on m. I draw this as a wiggle, ma. Now we are all done, okay? So the motion is constrained to move along this line, which makes an angle theta, but you have to consider this fictitious force. Now we write the force equations, okay? It is going down along the inclined. So mg sine theta plus ma cosine theta is equal to ma prime. And it's not going into the inclined or jumping out of the inclined. So r, so this is theta, r plus ma sine theta is equal to mg cosine theta. Okay? So let's number these equations. 1, 2, 3. Let's see, what are the knowns, what are the unknowns? R is we don't know. A, we don't know. And A prime, we don't know. This makes 3 unknowns, but we have 3 equations. Therefore, this is a system that is soluble. The rest is algebra, okay? So, for example, here, equation 3 times equation 3. I insert for R from 1 MA over sine theta plus MA sine theta is equal to mg cosine theta. So I multiply. So you see, I only have one unknown, one equation, so it's easily soluble. Multiply by sine theta. So m plus m sine square theta A is equal to mg cosine theta sine theta, and A is equal to mg cosine theta sine theta divided by m plus m sine square theta. Now that A is known, we can solve for A prime. Let me erase, or I can continue here. M's, I cancel M's. Okay. A prime equals g sine theta plus cosine theta times A, which is mg cosine theta sine theta divided by m plus. So if you take to g sine theta parenthesis 1 plus g sine theta is taken out. So it is m cosine square theta divided by m plus m sine square theta equals, when you put this thing upstairs, m sine square theta plus m cosine square theta is m. Therefore, the result is g sine theta times m plus m divided by m plus m sine square theta. So this is our A prime. Let me just all right. This is the solution. A goes wedge goes to the left with this acceleration, and A prime goes to the right with this acceleration. Does it make sense? First, let's check the dimension. G is already acceleration, so the rest should be dimensionless. Mass divided by mass. Okay, dimension is correct. And let's look at the limiting case. For example, if m is infinite, large or very much larger than m, what happens then? So if m over m goes to 0, A goes to 0 because you are dividing by m, and ignore little m with respect to the big M. So it is A prime is equal to A, which is g sine theta. In that case, the wedge does not move. For an infinitely heavy wedge, this thing, just like in our warm-up exercise, goes down. All right. Now, we can continue on this problem in many interesting ways, some of which I will leave to the quizzes. Okay. One thing is, what is the relation between A prime and A? Let me just erase this one. I don't need this. Oh. So 2 times multiply equation 2 by cosine theta. So mg sine cosine plus ma cosine square is equal to ma prime cosine. And multiply this thing by sine. And r sine theta is ma. So it is ma plus ma sine squared is mg sc. Let's add them. This thing cancels that. This plus that is simply ma, because cosine square plus sine square is 1. So we get m plus m a is equal to m a prime cosine theta. If you notice, this checks, right? Divide by m cosine theta, we have g sine theta, and multiply m plus n, we get this result. So far, you had studied in your lectures in the course kinematics and Newton's second law. This actually is the expression of conservation of momentum, but this will come later. So if we continue this series, we may come back to this again. So this is the conservation of momentum. One last thing I want to write is the relation between A prime and A, because after all, what is A prime? A prime is the acceleration as measured by an observer on the wedge. How does it look to a person on the ground? Now we can do that very easily. I am erasing this. Okay. So here is A prime. This is mass m with respect to wedge. This is the acceleration of m with respect to wedge. So this is wedge with respect to ground. It is going with A. Okay. So the mass accelerates with respect to ground with A. So this is A prime, and we know this is theta. So it's very easy to find. AY is equal to A prime y, which is A prime sine theta, and AX, the x component of A is shorter than the x component of A prime by A. So AX is A prime x minus A, which is A prime cosine theta minus A. Okay? All right. We will extend this problem now. Again, it's the general case, and we apply now an arbitrary force F in this direction. Now study the system again. So this one is theta R F. Now first let me start with a little bit force so that it's only a small change in the previous system. So I again assume it goes to the left. So R sine theta minus F is equal to MA. And if you look at our little mass m, there is the reaction force R, there is mg down. Since it's going to the left, I put the ma. Again, we write the equations. Going down means mg sine theta plus ma cosine theta is equal to ma prime and 3 ma sine theta plus r is equal to mg cosine theta. Since f is given, again the only unknowns are r, a, and a prime. So we can solve for this. M a sine theta plus, instead of r, I put f plus ma over sine theta. F plus ma over sine theta. That's equal to mg cosine theta. So one equation, one unknown, we can solve it. Okay. Ma sine square plus f plus big ma is mg c. So m plus big M plus m s square a is equal to mgsc minus f. Therefore, a is mgsc minus f over m plus m sine square theta. So this is when we have. Now let's get to a prime. A prime is again to be solved from here. A prime is equal to g sine theta plus a cosine theta. That's equal to g sine theta plus mg(s)c square minus fc divided by m plus ms square. Equals gs parenthesis 1, which I will write as m plus ms square gs is gone plus mc square over m plus s square minus fc over m plus ms square. Let me write it in, I'm erasing this part. That's equal to g sine theta m plus m divided by m plus m sine square theta. They have the same denominator, minus f cosine theta. Now this is interesting. Because you see, I'm erasing the algebra now. Let's look at the result and finish it. This is a prime down. We took positive. So if f is such that, f is equal to G tangent theta m plus m, then A prime down is equal to 0. You see, this is F0. We recovered beginning. And if F is larger than F0, A prime is negative. That means it's not going down, it's going up. So I can write this thing. Here, let me write A prime. Here, F. Here it is 0. Here it is F0. So when it is 0, you put there F0. Then you put your numbers here somewhere. So it comes down and up. That means F0 is a critical force because if you push it with a force greater than F0, the mass doesn't go down, it slides up. Okay? And I give you as an exercise also, if F is such that it is equal to that, which is mgc cosine theta, then you should work out that this turns out to be g sine theta, the warm-up exercise 1. Before I stop, I want to say something. Suppose we put friction here, okay, mu. I will not do it. But you know, I just tell you what happens. What happens is that instead of coming down and going up like this, you will have a range where it doesn't move, okay? So you will have... This system is interesting and obviously more complex, so I will stop here. But this was just to give you an idea. Thank you.